building where my office is. It's the soulless, windowless concrete structure on the edge of campus that looks like it was thrown up overnight in the 1960s. That's not actually true here on the Notre Dame campus, because mathematics is very blessed to be housed in the very beautiful Hurley building, which is located in the center of campus on the South Quad. So, why is this? Well, as you can tell if you visit the south atrium of the Hurley building, and you see the beautiful fixture, the globe, that I encourage everybody to visit if you have the chance, you will learn very quickly from walking around the atrium that actually Hurley building used to be the home of the School of Business. And in 2000, the School of Business built itself a fabulous, amazing, wonderful new facility, the Mendoza building, and they moved out and left Hurley Hall. And for some reason, I've never understood why, mathematics was the lucky beneficiary of this, the largesse of the Mendoza people. So in fact, prior to 2000, mathematics was housed in the soulless, windowless concrete slab on the periphery of campus. So why am I telling you all of this? Well, what I want to talk about a little bit is the scientific method. So I want to illustrate the scientific method by thinking about the Notre Dame math building. So what is the scientific method as it is traditionally presented? You make some observations. You go around the world and you see that mathematics departments are always in these terribly ugly buildings. That's the hypothesis you construct based on the observations. You test this with experiment, and when you come to the campus of Notre Dame, you discover that your hypothesis is incorrect. You draw the conclusion that you have to reject your hypothesis, and so you go up the arrows and you construct a new hypothesis. There's something missing from this presentation of the scientific method. Because, for example, you could go through this process with buildings in which math departments are housed, and you could draw the conclusion that, okay, my initial hypothesis was incorrect, I'll reject it, I'll make a new hypothesis. My new hypothesis is that mathematics departments are housed in soulless, ugly, concrete buildings unless they happen to be in northern Indiana. And you will very, very quickly have to reject that hypothesis because you'll go down the road to IUSB and you will see the beautiful Northside Hall where the math department is located there. What you really want to do when you're performing the scientific method is when you get to those up arrows, you don't just want to construct a new hypothesis, you want to ask, why was it that my original hypothesis failed? And use the answer to the question, why did it fail, to inform not just some arbitrary new hypothesis, but to inform a new hypothesis that has a much more reasonable chance of being the correct one. Maybe if you ask the why is Notre Dame mathematics department located in such a lovely building, you might form the hypothesis that math departments all around the world are in ugly, soulless concrete buildings on the edge of campus that were thrown up overnight in the late 1960s, unless they happen to have formerly been in those buildings and inherited nicer buildings from more prestigious departments or colleges or schools. And that would almost certainly be a hypothesis that would stand up to any amount of testing all around the country and the world. So the thing I hope that I'm going to be emphasizing as this talk goes on is that mathematics is not about solving ever harder differentiation problems or computing ever more complicated integrals. Mathematics is about asking the why of things and trying to increase our knowledge and increase our understanding from the why of phenomena that we observe. And I'm going to try and illustrate that with a couple of examples. But first, I want to do a warm-up exercise. So maybe a few of you, I think a total of 20 people, have a card and a pen. And what I want you to do on your card is to write down your birthday, just month and date, not year. But I wanted 40 people to participate in the experiment. So I want you to write down your birthday, and I want you to write down the birthday of someone else who is significant to you, maybe a spouse, maybe a son or daughter, maybe a mother or father. However,
for the two people colluding in the back there is to be no colluding in this. So Matthew and Annette, I suggest that you not pick your spouses as the second date that you put down. So basically what I want to do is I want to generate the birthdays of 40 randomly chosen people. And now that that's been done, I want to ask you all an intuition question. When Samantha shared with me the first draft of her introduction for my talk, there was a line in it, I promise you, you won't have to do any math in this talk. And I requested that that line be removed because, in fact, you are about to do some math. I am going to ask you an intuition question, and I want you to use your intuition, let your gut talk to you, and say what you think the answer to this question is. And the question is, there are 40 people in Jordan 101 at the moment. How likely is it that two of them share a birthday? Maybe it's less than 10%, maybe it's close to 25%, maybe it's like 50-50, maybe it's around 75%, maybe it's much more likely, maybe it's close to 90%. And I don't want anyone to take out their calculator. This is an intuition question, so let's just do a show of hands. How about option A? Yeah, we got no takers for option A. How about option B? We got quite a few takers for option B. 1, 2, 3, 4, 5, 6, something like 9. How about option C? A couple of takers, maybe 3, 4 takers. How about option D? Okay, a lot of people are leaning towards this actually being quite likely. How about option E? Okay, I'm noticing something about some of the people who are putting their hands up for option E. I mean, I've given a talk like this on a number of occasions. I don't think there have been ever this many math PhDs in the audience when I have given this talk. So I think the consensus was somewhere around D. Okay, let's do a calculation. And this time, you don't have to do the calculation. I'm going to do the calculation for you. So how likely is it that two people share a birthday? It turns out that's pretty hard to calculate. However, something very closely related is really easy to calculate. What's the probability that the 40 people actually have different birthdays? So the calculation for that is, well, the first person has 365 days to choose for their birthday. Forget about leap years. The second person then only has 364 options because the second person can't choose the same as the first person chose. The third person has 363. All the way down to the 40th person has 326. Those are the successful outcomes for this experiment where no two people share a birthday. What about total number of outcomes? Well, the first person has 365 choices for a birthday. So does the second. So does the third, all the way up to the 40th. And if you work out what this number is, this is not math, this is just computation, it turns out to be around 10%. So in fact, the probability that there is a coincidence when 40 people are gathered and they all reveal when their birthdays are, the probability is actually extremely high. It's 90%. I'm very curious to know, did we get a coincidence? So I'm going to just go around the room and have everybody call out loudly their two dates. And if you hear one of your dates called out by someone, just say, bingo.
February 23rd, September 24th.
10:15, 3:27.
We already have a coincidence. Okay, that didn't take long. And you know what? I was pretty confident that this wouldn't take long because I had done the math. And I knew that I was going to be 90% sure that there was going to be a coincidence. You know, actually, this has nothing to do with my talk. I was more than 90% sure because this calculation is based on the erroneous assumption that people's birthdays are uniformly distributed across the 365 days of the year. But in fact, you can look at the data from the Social Security Administration and see that this isn't true. There are some days on which very, very few people are born. Christmas Day is one of those. July 4th is another. These are days on which labor is never induced, for example, because there are many staff at medical institutions that are just not available to work that day. So there isn't a uniform distribution, and it turns out that the probability of coincidence only goes up as you move away from a uniform distribution. So this 90% was actually a floor on my estimate that I was going to see a coincidence, and it Didn't take very long. Okay, so have we learned anything? Probably not. We've just played with some numbers and discovered that there's a 90 yada yada, who cares? We've thought about the problem just purely as a computation. We're only actually going to learn something from this problem if we try to think about why did we get this surprisingly high answer. So let's put our intuition caps aside, and let's now put on our we're serious thinkers caps on. Anyone have any suggestions? Why is this probability so high? There's 40 people and there's 365 birthdays. That's like 1 in 9. How do I get 90%? Any thoughts as to why this should be the case?
Well, the only thing I can say is the alternative would be that everybody has a different birthday.
Right.
So if you think about that, that would seem, I don't know, it might seem unusual.
Because the pool of available birthdays is getting smaller and smaller as, if you have your 40 people, by the time the 30th person is selecting, well, they're now selecting from a much smaller pool of dates. That's definitely, that's driving the probability of coincidence up, the probability of no coincidence down. I think there's a more compelling reason. So, we have a suggestion.
Yeah, it seems like as you have 40 people, there's a lot more comparisons between each of those individual 40 people.
Yeah,
and there's a lot more possibilities for this to happen.
Right, so when I first heard about this problem, my thinking about it was, there's our answer, more than 90%. When I first thought about this problem, my thinking was, well, look, we're looking for a 1 in 365 event because we want two people's birthdays to fall on the same day. That's a 1 in 365 event. And I'm giving myself 40 shots at seeing this 1 in 365 chance. That's a pretty low probability. That's like a 9% probability. But that's completely not what I'm doing. This is absolutely the wrong way to think about the problem, because what I'm doing is I'm looking at pairs of people in the room. And for each pair of people, I'm asking, do you, as a pair of people, score a coincidence? And there are a lot more than 40 pairs of people in this room. In fact, the first person I pick can pair up with any of 39 other people. Then the second person can pair up with any of 38 other people to get a new collection of pairs. The third person can pair up with 37. It turns out that there are 780 pairs of people from among a collection of 40 people. And we're looking for a 1 in 365 event to occur among 780 repetitions. I kind of like my odds if that's the gambling event that I'm getting myself involved in. And we know it turns out to be a 90% likely probability. Just to illustrate this graphically, on the left is a graphic that you can't read, because this is a representation of 40 people with a line drawn between each pair of people. And there are so many lines that you can't even see them. This is an incredibly dense network. And it's inside this network of 780 pairs that I'm looking for a coincidence. Of course I got a coincidence. Just to show you what the graphic is representing, on the right-hand side, I've done the same with a collection of 15 people where there are about 135 pairs of connections. It's wonderful these days that when we do our mathematical computations, we have access to really high-powered computers that can draw nice graphs for us, that can calculate any number of things for us. So I was able to produce this graph last night. On the horizontal axis, what we're seeing is the number of people. And on the vertical axis, we're seeing a calculation of the probability that there is a coincidence among their birthdays. And you'll notice that if we have 40 people, then already we've gotten up to around 90%. But by the time we get up to 60 people, it's basically 100%. By the time we get to 23 people, it's already 50-50. This often goes under the name the birthday paradox. Paradox, apparent contradiction, but it's not a contradiction. because with 23 people in a room, you're looking at something like 250 comparisons. It's not at all surprising that you have a 50-50 chance of a coincidence among 250 comparisons. So this is just a toy problem, but this is illustrating a very important phenomenon not in mathematics, but a phenomenon in the real world. The phenomenon that random things tend to display a shocking amount of coincidence and clustering. So a couple of silly examples. What are the chances of 4 people having their birthdays spread across the 4 seasons? Pretty likely. Well, no, 9%. What are the chances of 12 people having their birthdays spread across all 12 of the months? Yeah, maybe not terribly likely, but it could happen. No, it couldn't. It's 0.005% likely. I generated some random birthdays last night, and I plotted which months they fell in. And what I found the first time I did it was that there was this shocking gap where nobody was born in June, July, and August, and 2 people were born in each of January, March, April, and October. I didn't like that, so I did it again. And I got an even more ridiculous distribution. This is not me making up randomness. This is random. This is life. And then I did it a third time, and I got a nice distribution. But again, there are these gaps and these anomalies. People who are well-versed in randomness would be able to look at a random string of digits or dates or birthdays and look at a string that a human has generated pretending to be random and instantly tell the difference. Because no human pretending to be generating a random string would ever dare to produce something like this. This is obviously not random. And that's what randomness is. Randomness is clustering. Here's an example that you will all, I imagine, be very, very familiar with. What is the probability that if you have any collection of people whatsoever, you can find some common time on their calendar for some social event or for some meeting? And I can tell you the answer is absolute 0. And 0 Kelvin. That is the probability. Okay. So let me give you another example of this phenomenon. Let me tell you about a conspiracy theory, or maybe not conspiracy theory, a recreational conjecture that was very popular a couple of years ago, that there is a collection of incredibly spooky, eerie coincidences between Abraham Lincoln and John Fitzgerald Kennedy. They were both elected to Congress in 46. Well, one in 1846, the other in 1946. They were both elected to the presidency in 60. They were both married in their 30s. Both got married to women in their 20s. They both lost a son while living in the White House. They were both assassinated on a Friday by a man with a 3-word, 15-letter name. They were both succeeded by a Southerner named Johnson, who was born in 09, one in 1809, the other in 1909. There are so many coincidences between the lives of Abraham Lincoln and John Fitzgerald Kennedy. You can go to the Wikipedia page, and you will find an astonishing list of coincidences. Is this a surprise? At first blush, it is. But the reality is, if you take any 2 people and you compare them across enough dimensions, you will, just by dumb luck, along some of those dimensions, get coincidences or get parallels. There are any number of ways in which Kennedy and Lincoln are completely unalike. Kennedy was never seen wearing a stovepipe hat. Kennedy shaved every morning. There's so many ways in which these are different people. But if you allow yourself enough dimensions across which you compare them, you will get your coincidences. In the early 1990s, the magazine Skeptical Inquirer, in 1992, they ran a spooky presidential coincidences competition where they invited readers to mimic this Lincoln-Kennedy conspiracy. And readers came up with 21 pairs of presidents. At that time, there were 40 presidents. From among the 40 presidents, there are something on the order of 800 pairs of them. Of course, you're going to find coincidences between 21 of them. It would be shocking if you didn't. So I hope you will take this as an illustration that you shouldn't let yourself be fooled by the apparent correlation between things, by apparent coincidences. And just to hammer home the point, and I don't know, am I beating a dead horse here, but I think what's coming up is amusing enough that it's worth going into. A statistician named Tyler Vegan a few years ago realized that if you plot the trend of something, there are only so many basic appearances that a trend plot can have. And so if you find enough things that you can plot their trends over time, you're going to find pairs of them that basically follow the same trend. And in his book, he put together some of the more unlikely pairs of phenomena that seem to trend with each other. So, for example, he found that the per capita consumption of mozzarella cheese correlates extremely well with civil engineering doctorates awarded. This is from the years 2000 to 2009. He found that US crude oil imports from Norway correlated perfectly with drivers killed in collisions with railway trains. He found that worldwide non-commercial space launches correlate with sociology doctorates awarded in the US. Divorce rate in Maine, per capita consumption of margarine. You can't argue with these graphs. Letters in the winning word of the Scripps National Spelling Bee versus number of people killed by venomous spiders. If the Scripps Spelling Bee this year is a long word, I am not going to the deserts in Arizona or New Mexico. I just don't trust based on this data. So what's the key takeaway from all this? The key takeaway is that you don't just do the computation and then walk away and say, I've done the computation, I hope I get an A on the homework for this. You ask the why of the result of the computation. And the why will very often give you a much, much deeper insight than simply the computation gave you. And this will give you some valuable information that you can take with you as you encounter other phenomenon. So, this was my first main example. I want to do two more examples in the time remaining. And each of them, just like the first, is going to begin with an intuition question for you all. So, first one, cantaloupes, it turns out, are normally 90% water. I have 50 pounds of cantaloupe, and I leave them out in the sun, so the water starts evaporating. And after some evaporation, they're now 80% water. So here is the gut check intuition question. At this point, what's the total weight of the cantaloupes? And I'm going to give you a few options. Close to 45 pounds, close to 35 pounds, close to 25, 15, 5. And this is a gut check, so no calculators. Let's just do a show of hands. Have I dropped down to 45 pounds? Quite well, I've dropped around like 10%. Have I dropped down to 35 pounds? Have I dropped to 25 pounds? Have I dropped to 15 pounds? And what about 5 pounds? Yeah, these last two are getting unlikely. So what I'm seeing here is that there's no consensus here. Nobody was interested in D or E, but A, B, and C both got a fair number of votes. Well, let's do the calculation. So my 50 pounds of cantaloupe consists of 5 pounds of pulp and 45 pounds of water. How do I know that? I know that because 5 is 10% of 50. I learned that in elementary school. Now, I know that after I have left them out in the sun for a while, what was the parameter of the problem? I've already forgotten. 80% water, yes. 80% water means 20% pulp. What is 5 20% of? Yeah, 5 is 20% of 25, which means that the total bulk must be 25. There's now 20 pounds of water, and the total weight has actually dropped all the way from 50 pounds down to 25 pounds, even though the percentage of water has just dropped ever so slightly from 90% down to 80%. So you suggested, you tentatively put your hand up for 45 pounds. What do you think went wrong with your thinking?
Well, I had the 5 pounds, and I mistakenly said that was 5 pounds, and I just subtracted that from the 50, and I got 45.
Right, you're thinking that just all the pulp went away.
Yeah, I did it backwards.
I think that what happens a lot when we encounter problems like this is that intuition or our thinking leads us astray a little bit, because we have two quantities here, the water and the pulp, and they are very, very different in measure. One of them is 5 pounds initially, the other is 45 pounds. You can't reason about the changes in these two quantities, treating them as if they are essentially the same. They are on different order of magnitudes, and that has to be taken into account as we try to reason about how they change. So I want to introduce this problem in part just to work my way up to what I really want to say in this example. But the other reason that I want to say this is that I want to show you this drawing from Charles Schultz. Okay, let me tell you a more serious problem that relates to this cantaloupe phenomenon. And again, this will be a test your intuition question. Maybe you're starting to build an intuition at this point, though. So this is a problem about drug testing. So the World Anti-Doping Agency conducts random tests on Olympic athletes for meldonium, which is a drug that's estimated to be used by 1 out of every 200 athletes. And this is a very accurate test. It's a 98% accurate test. What do I mean by that? I mean that 98% of the time that this meldonium is present, the test will record it. Very, very, very few false negatives. 98% of the time that the meldonium is not present in your body, the test will fail to detect it. In other words, there are very, very, very few false positives. Okay, so an athlete is selected at random. They test positive for meldonium. How likely is it that they're actually using this drug? So I've given a couple of options. And let's test our intuition. So I want everybody to look at this, think about it for a few seconds, and then we'll do a show of hands. Okay, is it quite likely? Is it 95% likely? We have a couple of takers for that. Is it around 80% likely? Quite a few more takers from that. Is it around 50% likely? Yeah, we have a few takers for that. I think we had more for 80%. Is it somewhat unlikely, around 20, 25%? Yeah, a nice few takers from that, but I see a lot of mathematicians in that group. Is it quite unlikely? I really hope this isn't the answer, because, come on, this is being marketed as a 98% accurate drug test. If it was 5% likely that the athlete was actually using the drug after testing positive, that really throws a wrench on what a 98% accurate test could mean. Well, let's see what the answer is. And I think what I'm going to do is I'm going to start by thinking about this problem in the wrong way. So here is the completely wrong way to think about this problem. We have the users of the drug, and we have the non-users of the drug. And when the users of the drug take the test, most of them test positive because it's an accurate test. And when the non-users of the drug test, most of them test negative because it's an accurate test. So the positives far, far, far outweigh the negatives. And okay, it's not going to be 95%, but it's certainly going to be something around 90%. What's wrong with this picture? What alarm bells are ringing when you see this picture?
There's a lot less users than one.
Yeah, this is a complete misrepresentation of the real situation where we know from other data that roughly 1 in 200 of the sample space are actually using this illegal drug. Here is the correct picture. We have a tiny, tiny, tiny parcel of users up in the corner, and most of those test positive. We have a huge sea of non-users, and only a small portion of them test positive. But because the number of non-users so far overwhelms the number of users, the collection of false positives is actually very, very large compared to the collection of true positives. And I'm not going to pull out my calculator and do the calculations, but I did them in advance, and I discovered that it's actually 19.75% likely that the user is in fact, or that the testee is in fact using this, this drug. This is an unfortunate result. It's unfortunate because we were using a test that was very accurate. But by thinking about the cantaloupes, we should be primed to realize that when you have a problem that involves two different populations that are very, very, very different sizes, the pulp versus the water, the users versus the non-users, you simply can't reason about these two populations putting them on the same level. They're orders of magnitude apart. This is not an incorrect or a contradictory result. This is simply a reality of the fact that having a really, really accurate way of detecting true positives and also a really, really accurate way of detecting true negatives is not going to translate into a test that has that same level of accuracy overall if there's a vast disparity between the number of users and the number of non-users. There's good news, though. The good news is, what is the first thing that happens when an athlete is tested by WADA and their test comes back positive? Retest. So normally when athletes give samples, they give two samples, an A sample and a B sample that are separate from each other. And if a laboratory tests sample A and finds positive, then sample B is sent to a different laboratory, so there's an independent test on the B sample. And the good news is that if you start drawing these pictures, taking into account the possibility of a second independent test, then these tests do, in fact, start to become significantly more accurate. I did the calculation and discovered that if two independent tests come back positive, then now we're getting close to the level of accuracy that the test actually promises. It's 92%, which is...
Sorry to interrupt you, but my first question before you gave that explanation was that, so this is just an example, right? You're quizzing us. I certainly hope the tests are actually more than 98% accurate. Because if they're 92%, that means 8% of people are going to be sanctioned and punished when they're innocent.
So I am now about to reveal that I am a mathematician. I do not, in fact, know what is the gold standard for testing. Super good, yes.
Never go on one test.
But isn't that testing predicated on assuming that there's an equal distribution as you put up? It's like the 98%, maybe when they designed that, was like we're assuming there's equal distribution of users and non-users. So in the way that they're establishing a true positive and a true negative is flawed, maybe because they didn't have an appropriate sample size.
I think though that the data on the accuracy can be created correctly if you have access to a population that you know for other reasons you know. For example, in the case of Meldonium, maybe they volunteered the information. I have been taking it, and for the good of science, I am going to allow myself to be a guinea pig for this test.
pretty sure I interpreted these two things incorrectly. If there are in fact two samples from one user or non-user, you're testing a sample, and it comes back positive, there's a 20% that sample is in,
There is a 20% chance that the person happens to be coming from this pool here.
but then when you test the second sample from the same person, is that 20% jumping up to 92%
Yes.
that person's a user? Okay.
Yeah.
All right.
And what would happen if you were to repeat the test using the same lab in addition to another lab with this same lab? I used to do chemical tests, and we had quality control. The reagents, they have to be, you have to have your control sample, and you're known.
Yeah.
If the same test were to be done in the same lab as a repeat, would it be exactly the same result?
It would depend on what was the factor that, if the result, let's say, was a false positive, what was led to the false positive? And if that factor is systemic to that lab, then maybe you would get no new information. At least moving to a different lab, that if there is a systemic reason why you're skewing in the error direction with this first lab, you hopefully won't see it in the second lab.
Sorry, my follow-up question is, if in fact the number of samples that you have gets you closer to this stated 98% accuracy rate, I'm sort of envisioning your birthday graph where the number of samples you eventually get, is it approaching 98%? And then
it is, yes.
So they say we have an infinite number of samples of one person. We think that we've got a 98% accuracy in our test. Okay.
Yes.
So you could take 3 or 4 or 5 or 6 samples and get more and more accurate.
Right, so that's going to increase your confidence interval, right? Like
Yeah.
the more, these are technical replicates, so, gotcha, okay.
Okay, so let me finish by giving one more, a quite different example. And again, I'm going to ask you for your intuition. A road network happens to be, in a particular place, happens to be typically congested. Okay, so what's the solution? You add some more roads to the network, and that's going to improve the congestion. Okay, so here's the intuition question. Obviously, or not so fast? And yeah, of course, not so fast. I want to tell you about a very, very interesting example that a German mathematician, engineer, statistician, Dietrich Brayes, came up with in the 1960s. In studying road networks, he realized that it's actually quite possible that if you have a road network that has a certain throughput of traffic, by adding more roads to the network, you can actually decrease the efficiency of that road network. And here is the example that Brayes came up with. So he was imagining a situation where you have a bunch of commuters who every day are going from, in the morning, are going from A to B. And there is this lake that they have to go around. And there are these two not particularly good roads where the throughput is depending on the amount of traffic that are currently on the road. So if there's T cars currently attempting to traverse, the time it takes to traverse is T over 400. Now there are also these two roads here where they are very wide, they're very nice, they never get congested. Doesn't matter what the traffic is, it always takes 15 minutes for the traffic to go through. And he asked himself the question, what happens if, let's say, 4,000 commuters are making this trip every day, and they know that they're the other 3,999 commuters, and they know the layouts of the roads, and they know the typical congestion on the roads? What's going to happen? Well, what he reasoned was, suppose 2,400 of the cars decide to take the upper route. What's going to happen? What's going to happen is that those people who are taking the upper route, they will take 6 minutes to do the first leg, and then 15 to do the second, which will take them 21 minutes. The 1,600 who go the other route, the lower route, they're going to go faster because they'll take 15 minutes to get to this point, and then they will take only 4 minutes to go along this slower part of the route, and that takes them a total of 19 minutes. This is not sustainable because some of these 2,400 people will say, you know what, it's in my interest to switch from going up to going down. Now, if 800 of them switch, then the whole situation will be just turned on its head, and there will still be an imbalance. But if 400 of them switch, then you will have 2,000 going up, 2,000 going down, and you will get an equilibrium day in, day out of the commuters separating themselves into 2,000 going north, 2,000 going south, and everybody getting to their destination in 20 minutes. Now, somebody in this town runs for election and he says, my platform is I'm going to make the journey from A to B faster. I'm going to invest all of the city's resources into building a super, super, super fast bridge that crosses the lake from these 2 points in the middle. And it's so fast that no matter how much traffic is going along, it's only going to take 2 minutes to cover that route. So this is adding this fabulous new highway in the middle of the network. Of course, it's going to improve the situation. It's going to make everybody's commute a little bit better. Well, let's see what happens. Same 4,000 cars during the rush hour going from A to B. And it turns out that no one will ever use this fixed 15-minute road from A to C. Why not? Because even if everybody, all 4,000 cars, go from A to D, it will only take them 10 minutes. And then they can get down to C in 2 minutes. So by going via D, they can get to C in 12 minutes worst case, which is better than the 15 minutes. And by the same token, no one is going to ever go directly from D to B because it's always better to go from D to C and then from C to B. So what does that mean? That means that essentially A to C and D to B are non-existent roads. Everybody is going to go from A to C to D to B. So this is a typo. Yes, everybody's going to go from A to D to C to B, and it's going to take everybody 22 minutes. So by building this new super fast bridge, we've actually managed to increase everybody's commuting time. So this would be just a nice, quirky example, but what I'm wanting to emphasize is that you can't just look at something like this and take it on face value. You have to explore the why of a situation like this. There's just a few minutes left, so I'm not going to say a huge amount about the why here. It seems like on a practical level, the bridge is just so efficient that it acts as an attractive nuisance. Everybody wants to get on this super fast bridge, and suddenly that's created congestion that there wasn't on the road AD and on the road AC. There's a deeper, there's a much more subtle why going on here. So when I say that the drivers will settle themselves into an equilibrium, what I'm talking about is something called a Nash equilibrium for a competitive game between these 4,000 drivers. The equilibrium that these drivers are settling themselves into is the equilibrium where nobody has any incentive to move away from the equilibrium because things will be worse for them. In the case where 2,400 drivers were going north before the bridge was built and 1,600 were going south, that's not an equilibrium because there are drivers going north who have an incentive to switch to going south. But once it settles to 2,000 going north and 2,000 going south, nobody has an incentive to move away from that equilibrium. Anyone who chooses to move away will do worse for themselves. In the same way, here, no one has an incentive to move away from the equilibrium. But that's 4,000 people acting as individuals, thinking about what's best for me in this situation. And we all know when we sit behind the wheel of our car, no matter how well-intentioned we are, you know what, we're thinking about we. We see that light turn amber, push down on the gas because we got to get through before it turns red, even if it gives a heart attack to somebody who's coming through in the other direction. Something about sitting behind the wheel of a car, I don't know. There's another notion of an equilibrium that a group of people could settle into, something called a Pareto optimal solution to a problem involving multiple agents. And that's a situation where everybody is doing as well as they possibly could, but not in a stable way. So what happens in this situation if 2,000 people decide to go north and 2,000 people decide to go south? Well, then everybody is getting from A to B in 20 minutes. That's great for everybody if everybody is working together and agreeing this is the solution. But unfortunately, this is leaving things open for one bad apple to exploit a gap in the system. Because if people split themselves into 2,000 up and 2,000 down, then this route here is 10 minutes. Did I do the math wrong? Okay, yes, in fact, yes, thank you, yes. I divided 2,000 by 400, and I got the answer 10. So if you ever had any doubt that I'm a mathematician, that doubt should now be erased. I cannot work with actual numbers. If 2,000 people go this route, then it only takes them 5 minutes to get from A to D. So a bad apple has the incentive to take this route for 5 minutes, then drop down here for 2 minutes, then move up here for 5 minutes, and make the entire journey in 12 minutes. That's not a sustainable change, because if everybody says, oh, I'm going to hop on that train, then suddenly everyone is taking 22 minutes. So if society acts cooperatively and tries to hunt for a Pareto optimal solution, we can all do better and we can all get to work in 20 minutes. But if we are acting as individuals trying to do as well as we possibly can for ourselves, then we end up in this Nash equilibrium where it actually takes 22 minutes. So the why in this case leads to some very, very deep and powerful mathematics, but also leads to some very deep and powerful economics. John Forbes Nash's Nobel Prize for Economics was awarded to him in large part for his work on the question of how do people find an equilibrium in a multi-person situation like this, where you have to balance the forces of competition and cooperation. We had a postdoc at the math department in Notre Dame a couple of years ago, Evan O'Doherty, and he's from San Francisco, and he was featured recently in the San Francisco Chronicle. There was a very nice profile of him, and so I subscribed to the San Francisco Chronicle in order to read the story about him, and I haven't canceled my subscription yet, so every day I get an email from the San Francisco Chronicle with news of interest to people in the Bay Area. And as I was preparing these slides, I was very surprised to see the story that I'm about to reveal to you. So Bray's paradox is not just some rarefied example that if you hunt hard enough, you're going to be able to find. It turns out that if you design road networks in any kind of sensible way, then there's actually a non-trivial probability, 15, 20%, that you're going to see an instance of Bray's paradox when you add some new networks to the road. And in fact, this is a story that appeared in the San Francisco Chronicle on October 27th, about a week ago. New lanes meant to speed up the Bay Area traffic, maybe slowing some drivers down. So there is hard data that shows that on a particular stretch of a highway near San Francisco, because the choice was made not to enhance the road, but in fact to add extra lanes to the road, to essentially make a second road that runs parallel to the first road, the net result has been that things have gotten worse for the typical driver going from A to B, where A and B happen to be, Santa Cruz and Palo Alto. I'm not sure which towns are involved. So I hope I have shown you with these examples that there is a great value to, when you encounter a situation that maybe throws up a little surprise, to not just say, okay, something surprising happened, and maybe I can do a computation and that will verify that the surprise happened. There is a great value to stepping back and saying, why did this happen? And this is what the business of mathematics almost entirely is. We are looking at situations where things are behaving often not the way we expect them to behave. And we have computations that show that they don't expect the way that they behave. And no one cares. Write that in a journal article. The journal article will never get accepted. What we want to know is, why do these strange things happen? How do they connect to other things? How do they inform us about looking at other aspects of the world, be it the real world, the mathematical world? So, yeah, I think I have nothing else left to say except Gravila Mahagat. Thank you very much for your attention. Go Irish. Enjoy the game tomorrow.
Thank you, David. Yes, we just have to announce the winner of today's drawing, which I'm so sorry if I butcher your name. Generoso Ruyo? Is that Generoso? Okay, I was going with the Spanish pronunciation there. So this is a College of Science beanie hat that perhaps you can use tomorrow during the game. Yes. Thanks for attending, everyone.